going to continue our discussion now that we hopefully have the skills of finding the derivative, right? Think about how we're using that primarily in the last chapter and last discussion, how to make tangent lines, right? Thinking about the derivative as the slope of our curve at that particular point, at that particular x value. Now we're going to start to get into some more applications, okay? All right, and so let's share the screen here, and we're going to get into the application use of the derivative, okay? All right, and so, right, remember from our last discussion, right, we introduced that derivative f prime at x, or in particular f prime at a at particular a, right, to be the slope of the curve f of x, right, for any x we identify, or, right, the slope of the tangent line at any point on the curve given by f of x, right? And so, depending on our function, of course, we could have our function, something like that. There's our function. And for any point we choose, we can imagine having a tangent line, right? Anywhere along that curve. And along that curve, of course, we might get a horizontal tangent line, the slope, that derivative equaling 0. We might have a negative value going back here. We might get a positive value. Okay. We can work backwards, but getting that kind of image, right? And so at each of those points, we can evaluate and see what that derivative, right? So f prime at a, right? That'd be some positive value. Its slope's going upwards. It will be a positive value for our slope, right? F prime at this point, b. Now that slope downwards, negative. And we can estimate how big, how negative that slope might be. This might be like a slope of -2. This would be a positive slope, +1, 1/2, whatever you want to call it, right? We can make those estimates more clearly with a better defined function in graph. So there's one last point here. Let's see. F prime at c, right? We get exactly 0. Horizontal line, no rise, just running left, right, 0. Okay. And so as we start to look at these graphs, okay, something that starts to jump out to us, I hope. Okay. As we're working on these, what we start to notice is that at maximums and or minimums of our function, right? These locations where we're reaching our peak, the value of our function is higher than all the other points around it, or falling down to a trough, the lowest point, right? At those maximums, at those minimums, what do we notice? The derivative is equal to zero, right? We're going to have a horizontal tangent line. Right, so just like I had identified at that point C here, the horizontal tangent line, zero derivative. Notice that this happens at kind of a minimum, right? Locally around that function is graph. That's the lowest point. That's the bottom of that trough, the bottom of the wave. Around it, all the other points start to go upwards. It might not be the lowest in the entire function. There still might be a minimum over here, but locally, it's the lowest point we can identify. Okay. And we start to look for those. Okay, where can that be if we don't have the graph handy? Where might that graph have a maximum or minimum? It's going to be when that derivative is equal to zero. Okay, so now we're going to kind of pick up this idea then that some of this language that what we call these critical numbers CN for short, critical numbers of a function these are values, numbers where the derivative is equal to zero or is undefined. Okay. All right. So for our critical numbers, we're thinking that f prime at x is equal to zero or f prime of x is undefined. And undefined most often for us means basically we get a zero in the denominator. Where's our function not defined? What can we not compute? Well, we get an error if I try to type it into my calculator. Okay. And so with those critical numbers, we typically start to look for maximums and minimums of the function at those critical numbers. Okay, because kind of thinking about the application, this chapter, this portion of work is all going to be about these applications. How are we using the derivative in our work mathematically? And I suppose we have a function that's going to model a physical aspect, right? Thinking about like maybe we have a model with everything going on with the pandemic, or maybe there's a model where it's like those number of people getting infected with COVID, right? Maybe there's a model for how that's increasing or hopefully now decreasing, right? Right. So maybe we have a function and we have, well, when is that function going to reach the maximum number of people infected, right? Before we start to implement the vaccine, before everybody gets vaccinated, right? Where's that maximum, where's that peak going to be before it starts to fall down? Or after everybody's gone through their safety measures, either got the vaccine, done whatever they need to do, okay? When it's going to be the minimum amount of infections that we can expect after those plans are put into place. So if we have some function that's going to mimic, that's going to model that information, we can start to then project, estimate, identify where those maximums, minimums may occur by looking at these curve numbers. Where is that derivative going to be equal to 0? Okay, and so again, those max and mins that we're talking about, these are locations on our graph where we're going to have that peak, have that trough, that lower part. And in our graph, it might not be necessarily the lowest everywhere, so we call that kind of a local minimum. If I just limit my view locally, just look at a small space, sometimes we call them neighborhood around our point. It's the lowest there, it's going to be a local minimum. We might have a case where we have a maximum, right? Local maximum might be points elsewhere that go higher. If it's the very highest, we call it an absolute maximum, absolute minimum. These extreme, right? Extreme values we can start to look for. And they start to appear on our functions, typically with these nice smooth curves before we start to get to those jagged, sharp turns. Another place where our derivative can be undefined. We're going to look to see where that derivative is equal to 0 at those critical numbers. Okay? And later in this discussion of topics, we're going to use that derivative once more to find those max mins, but also gives an idea of what that graph looks like. Visually already when I say, okay, I have the minimum, I'm already imagining that little drop into a drop. But the next one, I'm climbing the peak, I'm getting to the high point on my graph. So visually, we're going to build up ways to use this in hopes of graphing functions using these characteristics. Okay, as we start looking for max mins, we begin by looking for these critical numbers. Okay, and so we'll see some more applications of this and build this in, like I mentioned, with that graphing and whatnot as we go farther. Okay, all right, so there's a quick introduction. Looking for those critical numbers, find your derivative, set it equal to 0. You'll have your set of critical numbers.